first one is reflexive relation. Let A is a set A, B, C consisting of 3 elements and R subset of A cross A. If R is a subset of A cross A, then R is relation on A, means R is relation from A to A. Now, reflexive relation. The relation on A is said to be reflexive if A belongs to R. A belongs to R means this order pair is present in R. That means A is related with A. So, A belongs to R means A is related with A. So, the relation will be reflexive if every element is related with itself. A is related with A, B is related with B. This is the reflexive relation. That means the relation of one element with itself. The second is symmetric relation. The relation on A means R is a relation from A to A is said to be symmetric if AB belongs to R implies BA belongs to R. That means if A is related with B, then B must have relation with A. That is, it can be written in another form as if AB belongs to R. That means if A is related with B, then B is related with A. A or B means A is related with B. So, symmetric means if A has a relation with B, then B must have a relation. If A is related with B, but B is not related with A, then this is not symmetric relation. Next is transitive relation. The relation on A is said to be transitive relation if AB belongs to R, BC belongs to R. That means A is related with B, B is related with C, implies A must be related with C. This can be also written as, that is, if A is related with B and B is related with C, then A must be related with C. So, this relation is the transitive relation. Very important is the equivalence relation. A relation will be equivalence. A relation is said to be equivalence relation if it is reflexive, symmetric and transitive. If any relation satisfies 3 conditions, reflexive, symmetric and transitive, then the relation is known as equivalence relation. So, if you want to verify that the given relation is equivalence, that means you have to show the given relation is reflexive, symmetric and transitive. Antisymmetric relation. A relation is said to be antisymmetric if AB belongs to R, that means A has a relation with B. BA belongs to R, that means B has a relation with A, which results A is equal to B. That means if A is related with B and B is related with A, which implies A is equal to B. In case of symmetric, if A is related with B, then B is related with A. In case of relation, if A is related with B, then B is related with A. But difference between symmetric and antisymmetric. In order to show symmetric, you have to take A is related with B. You have to take, but you have to show that B is related with A. Take A is related with B, so B is related with A. But here A is related with B and B is related with A, which results for which we can show A is equal to B. Then the relation is antisymmetric. So, next 2 types of relations, partial ordering relation. Partial ordering means a relation which is reflexive, antisymmetric and transitive. Then the relation is partial ordering. So, compare equivalence relation. When a relation is reflexive, symmetric and transitive, then the relation is equivalence relation. Equivalence means it is reflexive, symmetric and transitive. But in case of partial ordering, reflexive, antisymmetric and transitive. So, if in these 2, common is reflexive and transitive. If it is symmetric, then equivalence. If it is antisymmetric, then is partial ordering. And the last is the total ordering or linear ordering relation. A relation which is partial ordering and either AB belongs to R or BA belongs to R. A relation should be partial ordering and between these 2, any one must be present in R. That means a relation is said to be total ordering if it is partial ordering. That means reflexive, antisymmetric and transitive. Then either A is related with B or B is related with A. Between these two, one element must present in that relation. Then the relation can be said total ordering or linear ordering. Now example, let A is equal to 1, 2, 3. That means here A, the cardinality of A is 3. That means cardinality of A cross A is equal to 9. That means there are 9 elements in A cross A. I have taken some examples here. The first one, R1 is here 1, 1, 2, 2, 3, 3, 1, 2, 2, 3. Look at here. 1 is related to 1, 2 is related to 2, 3 is related to 3. That means every element of set A are related with itself. So this is a reflexive relation. So first one is reflexive. But identity relation, every element is related with itself only. But in case of reflexive relation, you have to omit the word only. That means every element is related with itself. Here, every element of set A, 1, 2, 3 are related with themselves. That means 1 with 1, 2 with 2, 3 with 3. But here, 1, 2, 2, 3 are present. 1, 2, 2, 3 are present. Still, it is reflexive. But in case of identity relation, here, this cannot be considered an element of identity relation because 1 is not related to 2. Due to the presence of these two elements, the R1 cannot be identity relation. R2, 1, 2, 2, 1. This is symmetric relation. This is symmetric. And why? Why this is symmetric? In case of symmetric, if A is related to B, then B must be related to A. So here 1 is related to 2 and 2 is related to 1. And the third relation R3 is 1, 2, 2, 1, 1, 1, 2, 2. Here R3 is a relation. Here R3 is symmetric 1, 2, 2, 1. So this is symmetric and also transitive. How it is transitive? Suppose this is A, this is B, B, C. Look at here. A is related to B, B is related to C. That means you have to show for transitive A is related to C. That means 1, 1. Here is 1, 1. So this is also transitive. Again, look at here. 1, 2. 2, 2. This is A, this is B, and this is B, this is C. A, B, B, C. Then there should be AC. That means AC means 1, 2. So here is 1, 2. So this relation is symmetric and transitive, but not reflexive. Why it is not reflexive? Look at here. 1, 1 is present. 2, 2 is present. That means 1 is related to 1. 2 is related to 2. But 3 is not related with 3. So this is not reflexive. So this is not reflexive. And the next one is R4. Here is 1, 1, 2, 2, 3, 3. This is reflexive. This is symmetric. And this is also transitive. How? If this is A and B, A, B, B, A. Look at here how it is. It is clear reflexive. How it is symmetric. Suppose this is A, this is B. For symmetric, A is related to B and B is related to A. So A is 2, B is 2, 2, 2, B is 2, A is 2. So 2, 2. So these are the two elements. So one element can't be repeated in set. So we can write 2, 2. So this is reflexive, symmetric and transitive. So this is the example of equivalence relation. Equivalence means reflexive, symmetric and transitive. It is R5, 1, 1, 2, 2, 3, 3. Presence of these three is clear that this relation is reflexive. Again 1, 2, 2, 1. So this is symmetric. Now for transitive, look at here dear students. Here is 1, 1, A, B. And here is B, C. B is 1, B is 1. So A, B, B, C. There must be A, C. A, C means 1, 2. So here is 1, 2. Again, suppose this is A, this is B. And A, B, this is B, this is C. A, B, B, C. There must be SC. Here is SC, 1, 1. So this relation is also reflexive, symmetric and transitive. So this is also equivalence relation. Another example, R is a relation which is subset relations on sets. When there are two sets, there is a relation between the two sets that one set can be subset of another set. So the relation subset on sets is also relation. What type of a relation is this? Look at here. We have to test subset relations. Let A, B and C be three sets. First, we have to test it is reflexive. Now, the first condition is we know that every set is a subset of itself. So, if every set is a subset of itself, then A is a subset of A. That means this shows that one element has a relation with itself. A is related with A. So, this is reflexive. Next, to show symmetric. Symmetric means if A is related with B, then to show B is related with A. Let A is related with B. Here the relation is subset. That means let A is a subset of B. And to show B is a subset of A. But in general, if A is subset of B, then B is not subset of A. But the only condition where A is subset of B and B is subset of A is these two sets are equal. So here, if A is related with B, that means A is subset of B, and B is related with A, that means B is a subset of A. If A has a relation with B, B has a relation with A, the relation is a subset. So A is a subset of B and B is a subset of A, implies if A is subset of B, B is subset of A, then A is equal to B. So what happens here? If A is related with B and B is related with A, then the two elements are equal. So this is the condition of anti-symmetric relation. That means here this relation is anti-symmetric. Next, to test whether it is transitive or not. Transitive means A is related with B, B with C to show A with C. So let A is related with B. That means A is a subset of B. And B is related with C, means B is a subset of C, which implies from set theory, we know if A is a subset of B, B is a subset of C, then A is a subset of C, right? So this is here, A is a subset of C. Now, this is the condition of a transitive relation. That means this relation is transitive. So here the relation is reflexive, antisymmetric and transitive. That means this relation R is partial ordering. R is relation defined as less than or equal to on integers. Let A, B, C belongs to Z. That means these are three integers. The first case is we know that every relation is less than or equal to, greater than or equal to itself. So this is reflexive. Second is symmetric. Let A is less than or equal to B and B is less than or equal to A. So if A less than or equal to B and B less than or equal to A, this shows A is equal to B. So this is the condition of anti-symmetric. Third is let A less than or equal to B, B less than or equal to C. A is related with B, B is related with C, which implies A is less than or equal to C. So this is transitive. So if a relation which is reflexive, antisymmetric and transitive, so we have R is partial ordering relation. This is partial ordering relation. But what happens here? Look at here. A less than B means A is related to B, but A is related to B. So this which implies R is total ordering. R is a total ordering relation, because total ordering means it must be partial ordering relation first. Then second is either A is related to B or B is related to A. One important example, So that similarity of triangles is an equivalence relation. Similarity of triangles is a relation, but we have to show this relation is equivalence relation. But from the definition of equivalence relation, you know, in order to show it is equivalence relation, you have to show this is a reflexive, symmetric and transitive, right? So first to show this is reflexive. Let T be the set of all triangles. Here T is the set of all triangles, and T1, T2, T3, these three elements belongs to T. So T is the set of all triangles. That means all the elements in T are triangles. So we take three triangles. These three triangles are T1, T2, T3. First to show this is reflexive, we know that the relation is here similarity. We know every triangle is similar with itself, right? The triangle T1 is similar with T1. So what happens? One element is related with itself. So this is, which implies this is the, which implies the relation is reflexive. Second, let the triangle T1 is similar with T2. So if one triangle is similar with another, if one triangle is similar to the second triangle, then the second triangle is also similar to the first triangle. This is the condition of similarity. If one triangle is similar with another, then the second must be similar to the first. This is the concept of similarity. So if T1 is similar to T2, then T2 is also similar with T1. So what happens here? If A is related to B, B is related with A. So this implies the relation is symmetric. Next to show transitive. Transitive means A related to B, B with C, then A with C. Let T1 is related with T2. The relation here is similarity. Let T1 is related with T2. T2 has a relation with T3. That means T1 similar to T2, T2 similar to T3, which implies from condition of a triangle, from condition of a similarity of a triangle, if T1 similar to T2, T2 similar to T3, then T1 similar with T3. So this shows the relation is transitive. Hence, this is such a relation which is reflexive, symmetric and transitive. Hence, the relation is equivalence relation. Now, the important properties. Identity relation, I have already said, identity relation means every element will be related with itself always. Always the elements of that say are always one element will be related with itself. One element can't be related to others. But in case of reflexive, what happens? Every element is related with itself, and one element can also be related to the other. So this is the difference between identity and reflexive. Remind the important properties. Identity relation and identity relation is reflexive, symmetric, transitive. Universal relation is also reflexive, symmetric, transitive. Very important short questions for exam. These two are reflexive, symmetric and transitive. The third is a reflexive relation is not necessarily symmetric, may or may not be symmetric. Fourth is a relation R will be symmetric if R is equal to R inverse. That means when the relation is symmetric, then the relation is equal to its inverse, or when the relation is equal to its inverse, then the relation is symmetric. And the next condition next property is if R and S are two equivalence relations. Suppose there are two equivalence relations on a set, then the intersection of two equivalence relations, R and S are two equivalence relations, then the intersection, that means R intersection S is also equivalence relation, but the union is not necessarily equivalence relation. That means the intersection of two equivalence relations is equivalence relation, and the union may or may not be equivalence relation. And the last property is if R is equivalence relation, then R inverse is also equivalence relation on the same set. The question is prove that a relation R on a set A is symmetric if and only if R is equal to R inverse. So it's proof. Let R on A is symmetric. To show R is equal to R inverse. we know that two sets A and B are equal if A subset of B and B subset of A. So if R is equal to R inverse, that means we have to show, that is to show R is subset of R inverse and R inverse is subset of R. If A subset of B, B subset of A, then two sets are equal. Now, in order to show R is the subset of R inverse, one set can be subset of another if every element of R are present in R inverse. That means let AB is an element of R. If we can show this element belongs to R inverse, then R is the subset of R inverse. Let AB belongs to R, which implies let AB belongs to R, but given R is symmetric, that means BA belongs to R, because symmetric means if A is related to B, then B is related with A, which implies if BA belongs to R, then AB belongs to R inverse, because if XY belongs to R, then YX belongs to R inverse. So if BA belongs to R, then AB belongs to R inverse. Look at here, AB was element of R, now AB is element of R inverse, which implies every element of R is present in R inverse. So R subset of R inverse. First. Second thing, to show R inverse is a subset of R, let XY belongs to R inverse. If XY belongs to R inverse, then YX belongs to R. If XY belongs to R inverse, then YX belongs to R, which implies if YX belongs to R, but R is symmetric. If R is symmetric, YX belongs to R means XY belongs to R. Symmetric means AB, BA, YX, XY. So look at here, XY was element of R inverse. Now XY is element of R, which implies every element of this set are present here. That means R inverse subset of R. From these two, equation 1, equation 2, R is a subset of R inverse. R inverse is a subset of R. From these two, we get R is equal to R inverse. So what happens? We take R is symmetric, we show R is equal to R inverse, and the next part is to take R is equal to R inverse. Let R is equal to R inverse. To show R is symmetric, how can we show? Let AB belongs to R. Suppose AB belongs to R. In order to show R is symmetric, if A is related with B, then to show B is related with A. Now, which implies AB belongs to R inverse. Why? If AB belongs to R, but we have taken R is equal to R inverse. So if R is equal to R inverse, if AB belongs to R, then AB belongs to R inverse. And if AB belongs to R inverse, then BA belongs to R. If AB is in R inverse, then BA is in R. It's the definition of inverse relation. So what happens? AB belongs to R, BA belongs to R. A related with B and B is also related with A. So we find R is symmetric. Hence proved.